We have studied about the structure, bonding and aromaticity of benzene. Now we will study about the preparations of benzene. So let's start. Preparation of benzene. Okay. So the first one is cyclic polymerization of ethyne. We have already discussed this reaction when we were discussing about alkynes. So we will have three molecules of ethyne. Okay. They will be passed through red hot iron tube at 873 Kelvin, which is a very high temperature. So in this temperature, some reactions like this occurs. Okay, by these bond shifts. So what happens? This pi bond breaks and instead a single bond is formed between these two carbons. Here also this pi bond breaks and bond is formed between these two carbons, and similar for these two carbons. So we get benzene. Okay. The second method is decarboxylation. Okay. So how will it be formed? We had already studied decarboxylation when we were reading the preparation of alkanes, right? So we had seen that by decarboxylation of a carboxylic acid, we get an alkane with one carbon less. So to obtain benzene, we will have sodium salt of benzoic acid. Okay. Sodium salt of benzoic acid. We can write this as like this. O minus and Na plus. So sodium salt of benzoic acid on reacting with sodium hydroxide and calcium oxide and heat, it will form hydrocarbon with one carbon less. So it forms benzene. Okay. So decarboxylation of benzoic acid forms benzene. The third one is reduction of phenol. What is phenol? Phenol is basically hydroxybenzene, that is benzene with one OH group. This is phenol. Okay. So when phenol is reduced by passing it over heated zinc dust, okay, when vapors of phenol over heated zinc dust, we form benzene. Okay, and along with it we will have zinc oxide. Okay, so in the previous reaction also, along with benzene, we will get sodium carbonate. So these were the preparations of aromatic hydrocarbons. Now we will study the physical properties of aromatic hydrocarbons. Okay. So the first point is aromatic hydrocarbons is non-polar. Okay. Generally, we had seen that alkenes have a higher polarity than alkanes. But for benzene, this does not happen because all the double bonds of benzene are in resonance. Therefore, benzene is non-polar. The second point is benzene is a colorless liquid. Okay. So, aromatic hydrocarbons apart from benzene also, they are colorless liquids or solids with characteristic odor. Okay. So, aromatic hydrocarbons generally do have odor, even if it's not pleasant, but they do have odor. The next one is they are immiscible with water. So, of course, water is a polar solvent and aromatic hydrocarbons are non-polar. So, that is why they are immiscible with water but readily miscible with organic solvents. Okay. And the fourth point is they burn with a sooty flame. Okay. So these are the physical properties of aromatic hydrocarbons. Now we will discuss about their chemical properties. Chemical properties of aromatic hydrocarbons, but mostly we will discuss about benzene here. Okay. So, the first point is they undergo mostly electrophilic substitution reactions. Okay. Electrophilic substitution reactions are the major form of reactions that benzene undergoes. Since we had discussed that unlike major alkenes, benzene do not undergo addition reactions very readily because the double bonds in benzene are in resonance. Therefore, the major category of reactions that we will see for benzene are the electrophilic substitution reactions. In very extreme conditions, they may undergo addition reactions though. Okay. So, the second point is in special conditions, they may undergo addition and oxidation reactions. Okay. So, we will discuss about the general mechanism of electrophilic substitution reactions. Okay. Mechanism of electrophilic substitution reactions. So, there are three steps. The first step is generation of electrophile. Okay. So, first of all, we will have to generate the electrophile. Electrophile is represented like this, E plus. Why? Because electrophile means the species that loves electrons. Okay. So, previously we had also discussed about electrophiles when we were studying about alkenes and alkynes, that electrophiles are those species which reacts with electron rich compounds because they are themselves electron deficient. That is why we represent electrophiles with a positive charge. Similarly, there are nucleophiles which are attracted to electron deficient species because they themselves have a electron rich nature. Okay. So, they are represented by negative charge. So, here we will discuss about electrophiles. So, the first step is generation of electrophile. The second step is formation of carbocation intermediate. Okay. The second step is formation of carbocation intermediate. The third step will be removal of proton from carbocation intermediate. This step helps in the formation of double bond. Okay. So, let's start the steps. So, we will start with the first step, that is generation of electrophile. Okay. So, electrophiles can be generated by Lewis acids. Lewis acids are the compounds which can accept electrons. So, Lewis acids are used for the generation of electrophiles. For example, aluminium chloride AlCl3, FeCl3, BF3, FeBr3, etc. Okay. So, let's say there is a chlorine molecule and we have AlCl3. Okay. Now, Lewis acids can accept electrons. So, one chlorine atom takes the bonded electrons and goes here. So, it forms one Cl plus, that is called the chloronium ion and AlCl4 minus. Okay. So we have some alkyl halide, suppose, and we have AlCl3. So again this happens and we get CH3 plus, right? So a carbocation is formed here. This is also an electrophile, and as usual AlCl4 minus. Now if we have an acyl group, okay, acyl chloride, this is an acyl group, okay, CH3CO, and we have AlCl3. Now we have CH3 C double bond O plus and AlCl4 minus. Okay. So this is the method of generation of electrophile. We will discuss about the other two steps of this mechanism, and we will discuss about the reactions in the next lecture. Thank you.